What's up, guys? So today is Monday, the 27th. It is Memorial Day. So I'd like to just take a second to remember all those that sacrificed themselves for us. Yep, so we could be here today. So let's go ahead and jump back in where we left off, and I moved my setup around so that I actually can put my arms up on this desk, and I think it's gonna help out with my being able to type because it was really bad, and it was really bothering me too, not being able to type correctly. So I have my elbows back on, solid ground again, instead of just being not on anything solid. They make these things on Temu. I actually found they come out and extend the desk as a wrist rest, elbow rest rather, and forearm. So I might get a couple of those. We'll see. But I'm trying out different things to be more productive. And anyway, so let's pick up where we left off. And okay, so here's the deal. The deal is I previously had implemented this data transfer function to get rid of multi-line, just to reduce lines, because, well, when you're new at programming like I am, you get overwhelmed by the amount of lines, and just traversing through the code can be daunting, but that's just something I'm gonna have to deal with, and I don't want it to become a part of my operational philosophy that less lines is always the best, because it's not. And as a matter of fact, creating a function if it's 5 lines, maybe not even 5, if it's 5 to 10 lines, and you're doing it 100 times, it might make sense to reduce the to put that in a function. But there is overhead associated with created functions, and I want to see exactly what the overhead is with that, because that's something I was curious about, because I was actually gonna go back and undo the changes. I made these changes to data transfer function, and I'm just damn, I could just totally go back and revert all those changes. I could pick up an old commit or whatever, which I've never actually done before. Well, actually I did do merge. It's a different scenario. But anyway, I want to test the performance of creating just a function, because I was doing some Gemini prompts or AI prompts, whatever, and I was just asking various things about programming, and I was Gemini pointed out that there's overhead with creating a function, etc. I was actually asking about how much overhead is associated with passing in a large object into a function. And Gemini basically told me that passing a large object or a small object into a function is virtually the same, because it's creating just a reference to the object, and that the most overhead associated with a function is actually the creation of the function itself. So I don't know exactly how true that is, because you can't always trust AI, because AI, you know, is just not trustworthy. They get it right and they get it wrong. So we're gonna do time it, and we're going to we'll say the code is we're gonna just say def f, and it takes like, we just take one parameter, and then what it'll do is it will do x plus or 3, and we'll just say then return x, or rather x plus equals 3, and then return x. Okay, so and then we have to do, what is it? We just have to do number and globals. Number, and we'll do 10,000, and then we're gonna do globals, which is gonna be equal to globals. And I'm pretty sure that's all you have to do. And then we can run this and see if we get an error. Okay, so we did not get an error, but I'm gonna do a few different ones. Really, I want to do one that just creates a function and literally does nothing, just like the skeleton function. Then we're gonna do another one that is like, well, I'll let this one be the middle, and then we're gonna do one more. Well, no, we really don't have to do that. We just need these two, because yeah, I just want to see the difference between like a skeleton function creation. Well, actually, I'm wrong here. This is not what we want to do. I'm a little off right now. We actually want to create the function outside of it. We want to call the function. We want to see what's the overhead associated with calling the function, not creating the function. So, made a mistake there. Let's fix this. And so we're just going to call f. Very easy, actually. And then we'll create g, and g is going to take an x, and then we're going to do x plus equals 3, and then return x. Now this one we're gonna fix as well to just be the function call. It's gonna be just g. So g of x, and we just pass in 1 for this one, and now we can do print time it, and same thing up here. We'll do print time it. Alright, now okay, so you can see that there's a significant difference between calling f a bunch of times versus calling g, passing in 1 a bunch of times. So I actually do want to introduce an intermediary, and that one's just gonna do we'll just make this one h, and then h is going to just take in a parameter, but it's not gonna do anything. It's just gonna pass. And actually, I want to call this one G, and then this one H. So now we can just leave that one as it is, and then we'll create a new print time it, and it's going to do H, and we're going to pass in 1. So now H is going to be the one that does the calculation and then returns, and F is just going to pass, G takes in a parameter and then passes. So let's go ahead and run this and see what we get. Okay, so we have 0.000421, 0.000597, 0.000681. So we have an increase. So ultimately, let's see like the overhead associated with just creating a function, not creating a function, with calling a function that does nothing, that takes 0 parameters, is 1/10, 100th, 1000th. It's 4 10,000ths of a second, which is very low. But let's think about this for a second. A 10,000th of a second it's not a lot at all. It's extraordinarily fast, actually. I think like we would be concerned once we hit the threshold of like hundredths of a second. I think that's when you should like be concerned about performance differences. But if there is like, you know, if there's less than 100th of a second difference, then unless it's like a super critical part of code where performance is like absolutely like gets replicated or something, and then like that number becomes like exponentially large, I can understand, you know, optimizing performance, but you also want to like balance with just like common sense and readability and stuff. So I just wanted to be sure that creating a function wasn't, or calling a function wasn't you know, crazy expensive, and it looks like it's not. And so comparing it to whenever it takes in a parameter and then doesn't do anything, the number jumps up by almost 2,000th of a second. Well, actually 10, 100, or no, a tenth, a hundredth, a thousandth, a 10,000th, a 10,000th. So not even a thousandth, a 10,000th. So that's like nothing. And then we have H1, which does a few executions, a few calculations rather, and then returns an object. That one goes up again. Well, that one actually only goes up a tenth of a 10,000th, or I'm sorry, it goes up 1/10,000th of a second, which is nothing, dude. Like, it's just infinitesimally small. It's very small. So then, I guess if we really wanted to just, let's do one more, and to see if this, like, maybe it's exponential to where it might be very small when there's only a couple, but then when you have, well, in our instance, it only takes a couple parameters anyway. So like we'll do I, and then this one's gonna take X, Y, and Z. I think it takes like 3 parameters. Actually, let's pull it up and look at it, because you know, when you're doing a test, I don't want to be vague. I want to be exact. So let's. So it takes in 3, and it does 1, 2, 3, 4, 5, 6, 7. It does 7 lines of code. So let's just mimic that. Let's just do 7 lines of code. We'll do x dot append, and then we'll just append 1 to it. We'll do y plus equals 1, and then we'll do z. You know, what are we gonna do to z? We can just do z divided by, or I don't know. We'll just do z equals string, whatever. And now we'll do x dot remove, and then 1, y plus equals 2, and then we'll do z plus equals, or we'll just do minus equals, and then minus equals g. I don't even know if that's gonna work. Actually, that's silly. We'll just do plus equals g to add that. I don't know if. All right, so there we have 1, 2, 3, 4, 5, 6, and then we'll just return. Well, this one actually doesn't return anything, so then we'll just create this new variable, which we'll just call O, and then we'll equal it to true. So now we have 7 lines, 1, 2, 3, 4, 5, 6, 7, and let's go ahead and create a time it for it. So let's just copy this and go down here and do the I, and we're gonna pass in, let's create this list. L is gonna be this just a list of 1, 2, 3. So let's pass in this list, and then we're gonna have the y, which is gonna need to be a number, so we'll just pass in 5, and then z, which is going to be a string, so we'll just pass in, well, we'll pass in a tuple actually. So how about this? We'll do z equals z at 0, and then z equals, or z, well, we can't do that. We have to say, and then we'll do a equals z at 1. So there we go. And then this tuple is going to be z, so we'll have a tuple, which is going to also, it'll be just like a string, eggs, and then ham. Now let's, so we're passing in L5, and then we're gonna pass in Z as that tuple. And there we go. Okay, so let's see what we get now, if we get an error. Okay, so we don't get an error, but you can see the time it took to do F was 1, 2, 3, 4 decimal places. So that's the tens, the hundredths, the thousandths, the 10,000th, and then the 10,000th again, and then we move up to the 1,000th of a second, which is still extraordinarily small, and then it doubles to 2,000th of a second, which is still very small. And then finally, to compare it against the actual just like code being executed, let's do another time it, but this time we're just going to have no function call. We're just gonna do just the straight up code itself. So we'll do this same exact code, and now we can compare that let's go ahead and okay, that, all right. I don't know. Well, yeah, that's fine. Okay, so now let's run the code and see what it does. Okay, 4314, it says print time at x dot append 1, and then okay, and then it says unexpected indent. Okay, so everything works up until this line right here, and we have a y plus equals 1 unexpected indent. I don't understand why we have this. Indentation error here. Okay, invalid syntax, true. And then still indent error. So this is happening where? This is happening x append 1, and then it goes into time it goes into this function, and then return timer statement setup timer globals. And it's having an issue there. Okay. Statement setup timer globals. Time it number. And then it goes to compile it. And then it's y plus equals 1 unexpected indent. Okay. Why is this happening? I don't know. I always have trouble with time it for some reason. I just let me see if AI can help me with this, why we're getting this. indent error. Okay, why is the above throwing indent error? We divided search across multiple lines with a single string. Python interprets the indentation of each line within the string as part of the string itself, and since the indentation levels are inconsistent, it results in an indentation error. Python interprets the indentation of each line within the string as part of the string itself. So the indentation of each line within the string, okay, is part of the string itself, and since indentation levels are inconsistent, it results in an indentation error. Oh, okay, I think I see now. So I would have to do it like this, and then is that the issue? That may be why. And that does look prettier. Okay, no, but it still says unexpected indent. So that's because we're all the way like at the end. Okay, globals equals globals, but X is not defined. Okay, that's true actually. So we'll change this to be L, and then this is gonna be we'll do M equals 5, so then this will be M, and then Z is already assigned, so then we need to change this to L, this to M, and then A equals Z at 1. That should work, and then we're just assigning a variable at that point. Okay, so this should work, I think. M equals M plus 1, but it's saying, okay, but globals should pass in the M globals right here, because this is a global. So I'm a little bit confused as to what the issue is with this. Can I access a local variable M where it is not associated with a value? Do I have to say global M? I don't think that's the issue. Oh, that actually is the issue? Okay. I didn't know that. I didn't know you had to do that. Okay, let's try to run this now. Okay, string index is out of range. Global M, global Z, and oh yeah, we need to do global L. and we're still getting a the string index is out of range. Restroom time. Okay, so it's telling us that we have string index out of range. Okay, so like the only strings that we're dealing with here are so something with Z. So it's A being equal to Z at 1. How is that out of range of Z? Because if Z is string, and then eggs, and then ham, so this should be eggs. Because we're not modifying Z. I don't understand why this Z is... Oh, I'm an idiot. I'm an idiot, man. God, come on, Josh. Come on, man. Gotta do better than that, buddy. I'm like thinking it's something complicated. I have a problem with that. I will think that, you know, it's more complicated. You know, like, oh, I definitely got the simple syntax right. Well, no, not always. Sometimes you just messed up on the really simple syntax. Okay, so that took way longer than what I wanted it to, but anyway, so let's compare this now. So this is a similar block of code. We do append, and then we do plus equals, and then we do z equals z at 0, and then x remove, then we remove 1, then we do y plus equals 2, and then a equals z at 1, and then, well, this has got to be changed to, which is b. Alright, now a is equal to z at 1, and then o is equal to true. So this is exactly the same now. So now if we print it again, let's see, let's compare these last two, because this is the one we want to look at, is I and this time it where the same code is executed outside of a function. So if we just execute it straight up, it takes 0.0023 versus 0.0045. So you're trying to tell me that the function version is faster? That can't be right. 0.0023, 0.0045? No way, right? How's that the case? So either way though, it looks like a couple thousandth of a second is not gonna, I don't think, make or break either way. So I personally feel like we're fine to use to just go ahead and use the function, because if without the function, it's showing that it takes more time. And I don't know if that's because we're passing this, we're like running global, and like global has to do this. Maybe we'll add that line in. Let's do that. Let's add in global, and we're gonna pass in LMZ to where they're exactly the same. So we're gonna have to put this, well, I don't know, we might be able to leave that below it since alright, yeah, so even better, we're gonna remove the parameters and we're just gonna do global, and then we'll change this to be L, this to be M, and this is that tuple, so that's Z, and this is also gonna be the M, and this is gonna be that's fine. And then, oh, so LMBZ, let's see, LMB Z dot remove. Okay, yeah, this one needs to be it's supposed to be L. So LMB LMAO, LMB LMAO, LMAO. I didn't do that on purpose. Okay, so I take 0 position. Okay, that's because we forgot to change this. Duh. Alright, here we go. Now, okay, so it was the globals. So the globals keyword seems to take a, like, see, because beforehand we had the global, let's see, we had the actual code without the function. It doesn't matter. I'll just look at it how it is now. So it's 0.0062 and then 0.0065. So the difference is like almost nothing. There's almost no difference. So that would mean that the overhead of calling the function versus running the code independent of the function is only 1, 2, 3, so 10, 100,000th, 10,000th. It's only like 3, maybe 4 10,000ths of a second difference, which is, or 3.5 10,000th of a second, which is like nothing. Like that's almost nothing at all. So I have no issue with using the function now that I see the difference. And let's see, because so we have the blank function, which is 0.0008, and then 0.005 with a little bit, and then 0.001, and then 0.006. So from H to I, there was a little bit of a difference, and that's because of executing those other like 6 lines of code. So like the actual let's do one more. We'll add in, let's see, so we'll just put in a code that does pass, and we'll see the difference, because I mean that makes sense, right? We just do literally just pass, and then compare that to the function that does pass. So just pass is 0.00012, and then the function pass is 0.000 0.39. So that's 10 hundred thousandth. That's like almost 3,000th of a 3/10,000ths of a second difference. And that, I think, is the same difference between whenever we run I versus the actual code without the function. And let's see, 10 hundred thousandths, 10,000th. It was actually 100,000th of a difference. Well, this was almost virtually. This was even lower. Like that was that time. There was even less of a difference. So these are the first ones. These two right here, 0.0002 and then 0.0008. So that's 6/10,000th of a second, and then this difference is going to be 0.003, and then so it's virtually no different. This is like the 100,000th. Yeah. So there's like no, the overhead of using a function is so small. It gets so small. I see that now. So I feel fine using a function. Let me just to be like, so f does pass, so we did pass. Then we do g, and g just takes in. We'll make g just do x plus equals 3, and then we'll just do g, but we're just gonna do no function call and just x plus equals 3. So now, and then h, we're gonna do the same thing. H does the same thing except it returns x, which we don't return, so there's really no like comparison there. So we can just compare that to the one that precedes the h time it. Where it's not associated with the value. Okay. So this one is just going to be actually m, because it's just any number. Cannot access like a variable word is not associated with a value. But we pass in like the globals as the, you know. I don't understand why that doesn't work. Because we're using globals, like we use the globals keyword. So like, why would we have to say global? Why would we have to say global m? Why would that be a thing? Okay, it works now. But then that means we have to worry about like the global keyword overhead. So the first two are, one of them's in a function, one of them's outside of a function. That's only a 10,000th of a second's difference, and then this one is gonna be the g versus basically the same thing minus the global line. So in this case, the function does take significantly more 10th, 100th, 1000th, and then this one takes 10,000, so it takes like less than half. But that might have to do with the fact that that has to do with the fact that we're passing in a parameter versus calling it with global. So does that mean that calling it with global is like that much faster? So this is G, and then in this one we'll just do global M. Wait, this was the third one. So this 1, 2, and then so wait, 3 was actually the fastest. So this one we don't pass it in. I mean, we don't call it with global. So global 1, 2, 3, 4, 1, 2, 3, 4. So okay, yeah. So global keyword is actually what's making it is actually. Wait, 3 and then 4. 1, 2, 3, 4. So this one was much faster. This is the one where we did use global, and then 1, 2, 3 was a lot slower, and that's going to be the one where we did pass in the parameter instead of using global. Okay, so yeah, I was right. So if we use global here for G, so instead of this we'll just say global M, and then M is plus equals 3. What do we have going on here? So that's 1, 2, 3, and then this is gonna be 1, 2, 3. So G now just does global M. So these correspond to each other. This one is, let's do the same order. So we'll have non-function, then function, non-function, and then function. So this is going to be non-function, and then this one's going to be function. And let's get a div to divide these. So we have this section and this section, and then these. Okay, so these two. But this one stands by itself. So let's put some divs between this. You know I love my divs. Alright, that's a little better. So now we have, we'll just put no function, and then with function, and then so on and so forth. We'll do no function and then with function. So no function. So we'll get rid of this because we want to just compare the difference between function and non-function, and return actually messes that up. That's really the only thing we want to determine, is the overhead associated with creating a function. So if we have F, G, then we have I, we got our globals here. So we're gonna use the global keyword because I think that's faster. So this is just pass This one is small calc, and this one is middle calc. Or we just put more calculations, and then these are going to be globals, and then no function time it, and then this one's going to be function time it with function time it, and then this is going to be no function time it, and then this one will be with function time it. Okay, and then this one we have H and then I, but we removed H, so now we just have I, so let's remove this one. Alright, now this is going to be, the no function is going to get moved to the top, and then this one is going to be with function time it's. Alright, there we go. That's good. Okay, so let's review real quick and make sure we got this all written out correctly this time. So we import time it, and then this is going to be our pass function. This is going to be a small calc function. F is just pass. Then we have G, which takes in global M. And let's restructure. Well, no, we'll do that after. Let's call this L. This is going to be I, and then this is going to be T for tuples. So that's going to be better. So this is going to be lit L I T list integer tuple, and this one is going to be changed to the I for integer. So we have def G, which takes global I, and then we're going to do I plus equals 3. So this is the G, and then this is going to be changed to H, and this is going to be more calc function. Alright, now global lit L dot append M, which is going to be changed to I because that's the integer now, and then this is going to be equal to T. We're going to change that to say A because we're going to do A, and then list dot remove 1. M is going to be changed to I because it's integer. Blah blah blah. This is going to be changed to the tuple. L is equal to 1, 2, 3. I is equal to 5 for integer. T is equal to string eggs ham tuple. No function time it. Alright, here we go. It's going to be pass. No function time it. Pass with function time it. And then we do print time it pass just with no function, and then we print F, which does the pass function. Then we're gonna do, this is gonna be small calc no function time it, so it's just straight up executing this code, but this is gonna be changed to be I, and I just want to see if I can do this without having multi-lines, or if I have to do this multi-line, because I feel like this should work as it is. And then this is going to be the small calc with function time it, so this is going to be calling the G, so we have F and then G. G is the small calc function, and then we have the more calc function, or more calc no function time it rather, and this one just does all this stuff, which is going to be L I T. So this is going to be changed to I. This is going to be changed to A. It's going to be changed to I. And then this is going to be A is equal to T. And that's got to be T as well. Okay. So then this one does more calc with function timer, which is I, and that's gonna be LIALIA. Okay. And alright, I think that's it. I think we've got that one correctly coded. So it's probably going to throw an error right here because we're not doing global I, even though we're saying global equals globals right here. I don't understand why that wouldn't work. Alright, so let's try and do this again. Alright, let's just get rid of that and then let's run it. Okay, so way up here it's doing that. So if we change this back to multi-line, and then we do global I, and then run it again. $43.22. Alright, yeah, so it's right there. Same thing. So you have to, I don't understand why you have to pass in global when you're like should be H. Okay. Alright, there we go. So now, and let's do a new line. We'll do, and then after this one we want to print new line, and then again after these two, and then, well, that's the last one, so we don't have to do it. Okay, so now we have them separated. So you can see the difference here is 10th, 100th, 1000th, 10,000ths. So 4 10,000th of a second. Difference here is 10 100,000th. This is like almost identical for middle calc, small calc. And then this one is going to be the no function is a little bit faster than the H function. but it's still 10/100,000th, and it's only 4,000th. Okay, so 4,000ths of a second difference is for the longer one. So I'm honestly more inclined to just go off of the difference between the one with less calculation, because I feel like the variation in this longer calculation code section is like, it's due to the difference in time is not necessarily due to the function overhead, but more so just the variation of like the performance in like the actual the other calculations it's doing, because these two, especially this one, it's almost identical, and then this one is just, the difference is so small. Yeah, the overhead of creating a function is just super small. So I'm happy with this. I'm not gonna like overdo it. I already overdid it, but I'm actually happy with this conclusion. Okay, so this time it was different. So we are getting variation in the numbers. See, and now this time the third one was almost identical. So I guess we're at the point that where like the differences are so small that any sort of like a little hiccup in the calculation changes the numbers kind of drastically, which just goes to show that it happens so fast that it's like it's not worth worrying about. So the overall overhead of a function could be as low as like 10/100,000th, what, like 300,000th of a second, which is like insanely small. So now I know that. I didn't know exactly, you know, how much overhead was associated with the function, with not creating a function rather, but calling with a function versus calling without a function. But a reminder that calling using a function versus non-function with same code shows that overhead associated with using function is less than a few thousandths of a second. TLDR. Using a function requires almost zero overhead. Use them. So yeah, that's what I gather from that. So yeah, I would say it's totally worth the cost, and that's the ultimate question, is like, is it worth the cost? So function versus non-func performance, and this is on the 27th, and you know, it's just good to learn like things like that, to really know. I didn't really like know, so yeah, I felt like, I don't know, I feel like I wanted to really know that. So let's see. Oh, so I'm gonna take a little break because it's been an hour. I'll take a little 5-minute break and drink a little bit of coffee and come back and try to get some more done. Take a small break here. back. Let's. I'm gonna do a little bit more. Then I'm gonna call it quits for today because it is a holiday. But okay. So now we know that the overhead associated with calling a function is like virtually 0. So we're not going to undo those changes. So let's go to things to do, and we're gonna get rid of that. We're not gonna undo it. So we need to finish implementing the data transfer function in place of the multi-line process for appending to changed attribute list upon data point changes. So place of the multi-line process for appending to change attribute list. Alright, so we're going to do Control Shift F and research this append, and this lets me know that we're dealing with appending to the change attribute list. Alright, so we're just going to go one by one through these, and I'm probably going to knock all this out, and then I'm going to call it quits. So going to data transfer function, game object equals, or rather, custom append list object goes first, and that's going to be the self.change attribute list here. Then the game object is going to be none here because skeleton player data isn't part of the time tuple. So let's go ahead and minimize that. And where are we at here? Alright, so game object equals none. And then caltup is going to be, what's it going to be? It's going to be this right here. So it's time perf counter and s. Alright. Let's make sure we paste that in correctly. Looks like we did. Alright, and yeah, skeleton player data is indeed not in the time tuple. So now we can get rid of this line. And also this one. Alright, and let's keep going. Transfer function, cal object equals self.change attribute list. Game object is equal to none as well, and then caltup is going to be this tuple. So let's just copy that bad boy, paste it in, and then we can get rid of this line right here, and go to the next one. Just keep going one by one here. Alright. So it's going to be another one. This one is going to be the C1 change attribute list for the cal object. The game object is going to be none here. And then caltup is going to be equal to this tuple. So now we can go ahead and get rid of that. Go right here, get rid of that one. Alright. Data transfer function. Cal object is going to be equal to the self.change attribute list. Game object is going to be equal to the none, and then caltup is going to be the tuple. So let's put this in. There we go. So let's get rid of that. Cal object, game object, and caltup. And we'll just jump straight to this one since we saw it. Cal object. Why does it show it out of order? Oh, it doesn't. It just highlights cal object first, and I can't see that. All right. Game object equals, this one's going to be none as well, and cal tube is tuple, and there we go. Pasted that bad boy in. Get rid of that. Go here as well. Do the same thing again. Cal object equals self change attribute list. Game object equals none. Cal tube is going to be equal to this bad boy right here. So there we go. And let's bam, 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 and go up here, bam, bam, bam. There we go. Right yonder. I'm gonna add this one in as well. Cal object is gonna be the actual C1 change attribute list. Game object is gonna be equal to none, and then cal tube is gonna be this here tuple. So C1 change attribute list game object equals none. Cal tube is equal to this tuple, and yep, that should be it. Yep. Right. Alright, now we'll do data transfer function, and this is going to be cal object equals self change attribute list, and then game object, which equals none. Whoa. Whoa. Okay. Cal 2.
They're as real as you and me.
Alright, so we can get rid of this one.
They're always there. Watching.
Yeah, yeah, yeah.
Waiting.
Watching, waiting.
Here.
Uh-huh. I hear you. And then this is going to be the game object, which is going to be none. And then we're going to do the cal tube, and that's going to be listen. Just listen. That's all you have to do. Just listen, dude. Alright. Okay, this is custom timeless, so this one actually is gonna be, we're gonna pass the, oh yeah, I don't have it imported. Alright, so data transfer function, cal object is gonna be, and you can see I'm able to type again, at least for the most part. My wrists are like still kinda, I mean my elbows are still kinda hanging off, so like it's a little bit, a little bit off still, but much better. What's the game object going to be here? So we have ID. So we'll just add the self dot P1 game. Yeah, so we'll just add self dot game object, and that's gonna be equal to P1 game. Oh yeah, but we. I just realized that certain places I can't actually, I would have to import the game object, and I don't think I can actually import the game object. Like I can't. I know I can't. What? Well, that shouldn't be a problem though. Trying to think which file it was where I don't import the game object. I guess I'll cross that bridge when I get to it. So we'll just have to import Oh, humble? God, what a terrible, no, Jesus. Alright, son. It's terrible, eh? It's terrible, eh? Right, fucking wacky. Game object is gonna be self.game object, and then cal2 is gonna be. Oh yeah, now like I have to have my. Yeah, dude, I gotta get those elbow supports. I can see like it's all in the elbow. If I don't have like my elbow supported, my ability to type is virtually 0. Yeah, my typing power level goes from well over 9,000 to like 10 without my elbow being supported. So cal objects, game objects, game object, cal tube, and then yeah. So, because yeah, these do need a. is a skeleton deck. Yeah, that's not handled by that. So cal tube here is just gonna be. I am so ready to be done with this project, bro. I swear to God, you don't even understand. You have no clue, bro. I am desperate. When I say I'm desperate, bro, I'm like the guy on the side of the road begging for change. So desperate to be done with this project. Like, desperate, dude. 475. So we have to import this data transfer function, and then we'll go to 475. Alright. Now, data transfer function and cal object equals. So change attribute list. Game object equals. So this is game state. Okay, so this one is gonna be necessary. So wouldn't we just say self dot? Well, no, we should just say self, right? Because this is the game. Yeah, we just say self. I think. Yeah. All right, and then cal tube is equal to that here tuple, that here tuple, that there tuple. All right, now. I know I'm an idiot. I just gotta do it 10 times before I figure it out. You dig? So you have to read it up in. Yeah, we already do that in the function, so that's like the point of doing the function. Found your ass. Found your ass. Hiding. And this is going to be self, and then cal tube is going to be this here feller. This here fella right here. Such a sad song. She has a sad fate. For all you Final Fantasy fans out there. This is Eris's theme, I'm pretty sure, right? Yeah. Oh, this isn't always true. This is bug. This is a bug. See this? This isn't always true. Sometimes the see cal object change to be less append for bubble and reference. Okay. So this isn't always true. Shit. Okay. If adder name. Okay. Like skeleton clicked card is not. Skeleton click card is not in the time tube. Okay. So I'm realizing that this is not actually. This is not ideal code. I see bugs here. Yeah, so here's the deal. We are yeah, this is bugged. We're doing wrong here. This is not good. So we say adder name is equal to cal tube 2, right? But this is gonna be looking for skeleton click card in the time tube. But it's actually should be looking for clicked card. Okay. So I have to put this. We'll just put bugged system here. When handling adders such as skeleton clicked card, etc., the adder name assigned adder name string assigned here via the cal tube would be skeleton clicked card, but it is looking but that's not in the time tube. Say that's not the time tube. Clicked card is in the time tube and is what should be assigned to adder name string. And is what should be assigned to adder name string. Need to review all instances of data transfer func calls to see if I missed this in other places. Yeah, yep. So okay, So how do we fix this exactly? Um, well, I think like just the easiest all around fix would be to change the data transfer function to specially handle these few, because almost all of them are like one-to-one, but because like whenever we transfer, this is the adder name of what's being transferred, and I don't want to put clicked card when we're actually transferring skeleton click card. You know, it's a little bit disingenuous to say we're transferring click card. We're actually transferring skeleton click card, which is like the purpose of skeleton click card in the first place. Now so that but the timestamp is associated with clicked card because the skeleton represents the actual clicked card. So I don't think we should change like anything in here. I think that's valid. I think the place that's lacking and that needs to be fixed is here. So we need to add in some code, some logic to take care of that. So we'll put you know, here's something I want to do. I just realized I want to compare, like, generally, what is the performance of a for loop? What is the performance of an if? What is the performance of a while? Well, I mean, a while, like, I don't know how easy it would be to like measure that performance, but anyway, we'll skip while. But like variable assignment, class creation, reference assignment, you know, I would like to see, you know, what Python structure, like those, you know, these used over and over again, like terminology, if, for, you know, variable assignment, etc., function creation versus class assignment. I would like to see how they compare to each other as far as which one takes the longest. If like that might just be moot though, because based on my testing the function call, that was like very low. That was like so low. And defining functions, you don't do that a lot. Creating classes, you don't really do that a lot. So that would actually be pointless. It's not like you can get around reference assignments and stuff. You have to do it. So why would you even test that performance? It's going to be so minimal, it's just going to be a waste of time. I mean, it wasn't a waste of time to compare actual code versus code executed through a function. I think that was worth testing. And I just don't think it would be worth it anywhere else. You know what I'm saying? I think like we did enough testing. I don't think we should test anymore. So I'm just gonna throw that little piece of trash that I just created in my mind. Throw it away. It's a trash can. Because that's wasted time. Alright, so bug system here. Let's get rid of this and we'll fix it. So if adder name is in time tube, we'll then say well, hold up. If game object is not equal to none, doesn't that mean that now we know that it is in a time tube? I mean, yep, that should be established. Yeah, so yep, we definitely don't need this line anymore because we have all of the function calls tailored one-to-one so that you know, and I will put a note here to represent so that we know this. Let me just put this note 527.24. Say instead of checking if adder name string in time tube, we individually assessed each data transfer function call throughout the project to pass game object equal to none in the case it's not in time tube. Therefore, all we need to check for in this function to determine if adder is in time tube is to see if game object is equal to none, or if it's not equal to none. True. Okay, so we can get rid of this, and then so yeah. String equal to 2, and then set out a game object time string. All right, so now we need to add in if adder name string. And what is it, 0 to 9 for skeleton? 0 to 9 is equal to skeleton. Then, or really we could just say, to like be even more simple, we could say if skeleton in adder name string. Because like, but doesn't that mean no, actually that might take longer, right? Because if we're checking to see if like this string exists within a larger string, how exactly does that work? Like, what exactly happens in the background? I'm gonna ask Gemini, and I'll put versus if adder name string 0 to 9 is equal to skeleton. So let's compare. Let's see what exactly happens in the background here. Let's ask ChatGPT. What exactly happens in the background? This line of code is a conditional statement that checks if the substring skeleton is present within the string variable adder name string. Here's what happens in the background. The in operator is used to check if the left operand, the substring skeleton, is contained within the right operand. Okay, a skeleton is found within a name string. Okay. Right, like, okay, but on a deeper level, what methodology does Python use to determine if that string is in the other string? At a deeper level, Python uses an algorithm to determine if one string is contained within another string. The specific algorithm used is typically a variation of the substring search. To determine if one string is contained within another string, the specific algorithm used is typically a variation of the substring search algorithm, which is optimized for efficiency. In Python's case, the in operator for strings likely uses some form of the substring search algorithm. The in. Okay. The exact implementation may vary depending on factors such as the version of Python being used in. Okay. One common substring search algorithm is the Knuth-Morris-Pratt algorithm, which is known for its efficiency in searching for substrings within strings. KMP works by pre-computing a partial match table based on the substring being searched for, which allows it to skip comparisons in certain cases, leading to improved performance. Python's implementation may use KMP or another efficient algorithm to determine if a substring exists within a string. Okay, give me an example of KMP. Here's a simple example of the Knuth-Morris-Pratt algorithm. So table is equal to, oh god, reading code is just, goodness gracious. Goodness gracious, goodness gracious. Alright, let's build partial match table pattern. It builds the partial match table for the KMP. So table is equal to 0 index times length of the pattern. And then I and then j is equal to 0, 1. Okay, while j is less than the length of the pattern. While j is less than the length of the pattern. Let's just say 9 right here. So while 1 is less than 9, if the pattern at I, so at 0, is equal to the pattern at j, so this would be s and then k, so s and then k. Am I reading that right? If, because 1 is less than the length of 9, or is less than 9, and then if pattern at I, which would be at 0, so that would be s, is equal to pattern at j, which is going to be at index 1, which is going to be k. So those are not the same, so it's going to do else. And then if I is not equal to 0, so pattern at I is equal to 0, okay, so s is equal to k, okay, else if I is not equal to 0, well it is equal to 0 at this point, then table at j, table at index 1 is equal to 0. Table at index 1 is equal to 0. And then j is plus equal 1, so now j is 2. And then it says while while 2 is less than 9, if pattern I, so I is still equal to 0, so this is still searching the first one. S is equal to I think Gemini mistyped this. I think what it's meaning to say here is like pattern 1 versus pattern 2, being like pattern 1 is like the string that you're comparing two different strings. So I think what it meant to do here was to say that this is the first pattern, this is the first string, and then this is the second string. Like, I think anyway, because then it would be comparing the first letter of the first string to the first letter of the second string. And then if there wasn't a match, then it would be comparing the first letter of the first string. Hold up, so pattern I is equal to pattern J. Or maybe it does have it right, because that wouldn't make sense either. If it was the string 1 at 0, and that doesn't make sense either, because why would the string at index 1 like be the same as the one at index 0? It's kind of confusing. I don't understand, but anyway, let's just run through this. So at this point, I is still equal to 0, J is equal to 2. So while 2 is less than 9, if pattern at I, which is pattern at I is going to be S is equal to pattern at J, which is going to be E. It's going to say no, it's going to go to else. And then if I is not equal to 0, which is not true, I is equal to 0, then else table J, table at 2 equals 0. Okay, so table at 2 is equal to 0. So before we had table at 1, and then J is plus equal to 1, so now J is equal to 3. I don't understand this. I don't understand how this is finding a string within another string. 3 minus 9 pattern I SKE, or it's gonna be S and then L. Okay, so let's just, it's gonna keep going all the way through, and then like what happens? Oh, so there's way more to this. Damn, that's complicated. Wow, that's really complicated, dude. That's a lot. Like when you just use in, this is what happens. Like when you're using in, so in is gonna be very costly. So basically that's what I'm learning here, is that the broader thing is in is going to be very costly because of all this that has to happen. If this is everything that's happening in the background, that's a lot of logic. So I think that using in versus this is going to be a lot faster, meaning that if we just do if adder name string at 0 through 9 is equal to skeleton, that's going to be a lot better than doing if skeleton in adder name string. And let's just ask Gemini straight up, because I'm not trying to learn all that, you know. Let's see, if skeleton in adder name string versus if adder name string is equal to skeleton, performance. Comparing the performance of skeleton in adder name string versus adder name string 0 to 9 is equal to skeleton involves considering the underlying operations. This uses Python built into substring search functionality. It internally utilizes an algorithm like the Knuth-Morris-Pratt algorithm, or similar, to efficiently search for the substring skeleton within adder name. So it's optimized and efficient for substring searches. And then adder name string 0 through 9 equals skeleton. This extracts a substring of length 9 from the adder name string, starting at index 0, and compares it to skeleton. It involves slicing the string, so this would be 0s, 1k, 2e, 3l, 4E, 5T, 6O, 7N. Oh, it's not 0, they're 9. So that's a bug. That's to cut off P1 or P2 plus skeleton. So it'd be P1 underscore skeleton. But like, wait, that's hold on a minute. skeleton. No, that is right, man. I'm an idiot. I'm dumb. skeleton. So that's 8. So from 0 to 9 is length 8. It's the same thing. It's the same exact thing, Joshua. So sorry. Yeah, real slow. It's okay. First word skeleton in outer name string. Really? This most slicing the string, then comparing the exact substring with skeleton. This first officially expects exception which occurs additional varied converted first word. Really? Let me compare that, because I'm calling bullshit on that. This is going to be an easy way to test this. So let's I'm actually going to stop after this. But okay, so let's go test this real quick. Let's go to test reminders and alright, so let's recreate some more of these. Alright, you like that beat? You like that beat I just made? There we go. Okay, so we're gonna do not that. Let's go back over here and let's do this. Control tab to get me there quicker. Now, and this is gonna be import time it. So let's just do import time it, and then we're gonna do print time it dot time it, and then we're gonna put this inside of there, and this will be 1, 2, 3, and say if skeleton in an attr name string, and then we'll make attr name string equals skeleton clicked card. Okay, and just to make sure we spelled skeleton right. Yeah, we did. Okay, so if skeleton is in attr name string, and then we're gonna do what's it, number of globals equals globals, and then number equals 1,000, and then we'll just copy this whole thing. That, copy that one, replace this line with that one. So if attr, we'll just do print true, or we'll just put pass. That's all, because we just want to know the speed of like the actual if condition logic execution time. So this one is going to be slice, and this one will be in, and now skeleton attr name string pass, and then globals number equals 10,000. Slice is print time at a time it if attr name string 0 through 9 is equal to skeleton pass. Okay. Those never close. 4369. Oh. Okay, hold on. There we go. Time it skeleton and attr name string pass, and then 1, 2, 3 comma global dot is equal to globals, and then number is 10,000, and then slice. Let's check this. Okay, so it looks like in actually did smoke the slice, which is surprising to me, honestly. I thought that, I guess because you have to do like it does them one digit at a time, it slices them, and then it concatenates them, and then it checks them, as to where, I mean, honestly, I still don't understand how that in is faster than that, because that seems relatively like fast, as opposed to a different doing it like slicing. If you were to just like slice 0 through 9, that's just 9, you know, like you're grabbing each one, you're grabbing at 0, you're grabbing 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you're, I guess then you have to add, you say like new string equals like at 0 plus at 1, and then you have to say new string equals that string plus so on and so forth. You see what I'm saying? Does that make sense? Like you have to extract them one at a time, and then you have to add them together one at a time. Um, so actually I need to understand that better, like how exactly slice works in the background. So that's just gonna go in my like things to learn, and this is gonna be slicing. And we're gonna say how does slicing actually work in the background? And then we're going to do the same thing. We want to learn about in. How does in statement actually work in the background? Yeah, so that's something that is probably worth learning at least a little bit. Okay, to be that, you know, that like next level guy that really understands that sort of thing. I like to take advantage of being into something. Like, I mean, I like to take advantage of learning something when I'm dealing with it versus just learning it at any random point in time. Because when you don't have like a context to actually like learn it, there's not much of a motivation. You know what I mean? Like, it's not exciting to just learn about how in works in this new three guy algorithm thing. You're just gonna like be bored to death. But if you're working on a project and you're using in, and then you're like, well, how does that compare performance-wise to like using a slice? Now you have the opportunity to learn about both of those things and to be more excited about it than you would have been if you would have just said, hey, I want to learn this because I feel like I'll probably need to know this one day. So anyway, yeah, but I'm not gonna learn it right now. But I do want to say no, I'm gonna stop there. I'm not gonna go any further because it is holiday and I'm actually ready to be done, even though we probably only went for, it's been 2 hours. Forgot to reactivate my screen, but that's okay. It's no big deal. So let's just run this a couple more times and see. And yeah, so it looks like in is significantly faster than slice. Okay, not that time. That's weird. So these are just such small calculations. I think the variation is going to be higher in the time because it's so small. So yeah, but consistently, in is extremely faster than in. I mean, in is extremely faster than slice. So I'll just copy this and we'll put result, and then this equals, and we'll put this up here as well. So we have result equals such and such, and I gotta use the restroom real quick. I'll be right back. Okay, let's go ahead and wrap this up because I'm pretty much done. Um, but now we know that in is much faster than slice. In versus slice. 5, 27, 24. So we did not think that that was going to be the case, which I'm pretty sure there's some places in the game where I slice versus in determined that there are various places where I use a slice string equal to string and that using in is actually much more efficient. Did a test on this 52724 see test reminders.txt. Which is an exact case scenario match, so it should apply to these instances. Do a complete project base search place. Okay, and then let's go back to alright, so then we're gonna say if skeleton is in adder name string, yeah, we found out that in is much faster. See test. Then the adder name is gonna be let's think about this. So the adder name is gonna be changed to, well, we basically just want to cut the skeleton off of it, right? So instead of skeleton click card, it would just be clicked card. And then I'm going to put, can we just cut skeleton off of the string to get the non-skeleton version? but would this work for all skeleton adders? Meaning, if some are like, well, see, like in the case of skeleton clickable card lists, well, actually that raises the question of should these be skeleton? Lines. Should these be skeleton? Or should we use the non-skeleton naming for time to, as is done with clicked card? If so, be sure to change other time to in file. And then just got skeleton off this string to get the non-skeleton version of this for all skeleton recipe. If some are transferred in terms of, meaning if some adders in time to need to remain with skeleton name versus without arbitrary. Yeah, so then that means C line 21 is 22 above, and determine this first before deciding here. And yeah, so then we're gonna go ahead and stop. So we have a couple little like kinks to work out with this system, but overall we pretty much got it figured out, and we're like, we only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That don't count, so there's 13. We only have like 13 more of these to convert, so that's like not even a minute a piece, so that's like 10 minutes of work. And then this is gonna just be like 5 minutes of work, so it's 15. And then this is just gonna be like another 5 minutes, so it's like 20 minutes of work to be done with this function and the implementation of this function. And then we'll be able to move on to back like from our where we got deviated, which is handling that race condition with change attribute list. And that meant that we were going to implement that lock inside of the data transfer function, and that's where we got sidetracked. So I'll just put pick back up here after finish number 1. Yep, so let's go ahead and close all this out and go back to our devlog, and we'll just put stopped in change attribute list file, and this was to 420, and we did all right today. Not the worst, not the best, but we continued implementing data transfer function. And finalizing associated logic in place of multi-line changed attribute list appends. So yeah, and this is gonna be 420 to 425. We're gonna stage and commit those changes because I don't want to lose any of my work just in case something were to go wrong. And this was, yeah, to 425. So this is how many hours? 45. That's 3, not quite 3, 2 and 2.5 basically. So yeah, 2.5. We'll just say 2.5 hours. And so that's pretty good. 2.5 hours on a holiday. I'm happy with that. Alright, so now let's make sure we're on the right branch, or project directory rather, and we are. Deprogramming projects Canasta is the root, and then we'll do git branch to ensure we're on the right branch. Should be secondary, which we are, so we'll do git add dot to add everything. We can ignore these LF warnings, so then we can do git commit -m, and then get rid of these quotations now. And that looks like it's it for those. We did 8 files change, 251 insertions, and 46 deletions, and that was all in the test file. So we're gonna git push Canasta and then secondary, and there we go. Alright, so there we go. We pushed to the remote repository. Looks like everything worked as intended. Now we can go to our programming. My boy Joey got a cameo. So we're going to copy this Canasta, go to the backup, delete the old backup, paste in the new one. We'll ignore this pop-up because who cares about those. And go to text, go to devlog, and we'll check to see if it reflects today's changes, which it does because today's the 27th. Back out, change the date to the 27th to reflect today's date, as the last time the local backup was updated. And